Hi folks, I hope you've had a fantastic weekend. We're starting section 15.8 today. This is the unit on triple integrals and spherical coordinates. Before we get started, I just want to remind a couple of people a few things here. This is the last day of material that will be on test 2. We are not covering 15.9, even though there's another section in the chapter. This is the last day of material that will be on test 2. I have posted a practice test on Canvas. We'll go over that practice test on Wednesday as part of a review session. There is no class on Friday. We have a 3-day weekend coming up. But then Monday will be the test. So the test is a week from today. The material that is on that test stops today. So you have a full week to get ready for that test. Use it wisely. Ask questions. Make use of my office hours. Anything I can do to help between now and next Monday, I'm here for you. Okay? Let's go ahead and get started. Spherical coordinates are a three-dimensional polar system that involves an angle from the x-axis and an angle from the z-axis. You'll often find this system used in aerospace when you talk about, changing the yaw, changing the pitch of a plane. You have this plane that can change in multiple ways. Stage lighting is also interestingly a field that uses spherical coordinates a lot, where you have these lights heading up here that can rotate up and down on the stage and left and right on the stage, so that in order to aim at any position on the stage, spotlighting. So there are specialty fields that use spherical coordinates extensively. Some of you will use this quite a bit, and some of you will use this only occasionally, but let's go ahead and take a look at it anyway. A point in space has a triple of coordinates. The first coordinate is the Greek letter rho, which represents the distance to the origin. Since it's in three-dimensional space, it's the distance is the square root of x squared plus y squared plus z squared, or rho squared equals x squared plus y squared plus z squared. Theta is the angle from the positive x-axis, going around this way. And phi is the angle from the positive z-axis, and we restrict phi to only going from the North Pole down to the South Pole. We do not let phi go back behind the South Pole, so that phi covers this piece of a sphere. And if we want the entire sphere, we get the entire sphere by rotating that around, if that makes any sense. We don't let phi be an entire circle and then rotate it around, because then it will rotate over itself. So that's the idea. Okay? So let's try an example. Oh, before we get to the example, here are the conversion formulas we're going to need to convert into spherical coordinates. X is equal to rho cosine theta sine of phi. Y is equal to rho sine theta sine phi. And Z is equal to rho cosine phi. So, I don't know how you want to try to remember this, but theta, the one that changes between x and y, let me go back to the previous slide, is the angle that moves in the xy plane. And so as it moves in the xy plane, the y coordinate changes. And then phi is the angle that moves from the z-axis towards the xy plane. And so as phi changes, it starts on the z-axis and then moves down towards the xy plane. And then we talked about this formula already. This is just a distance formula. that the distance from a point to the origin is the square root of x squared plus y squared plus z squared. This is that formula just with both sides squared. Okay? And when we integrate in spherical coordinates, we replace x with sine phi cosine theta, rho sine phi cosine theta, or rho cosine theta sine phi. We replace y with rho sine phi sine theta. We replace z with rho cosine phi. And then in polar coordinates, we multiplied by r. In spherical coordinates, we have to multiply by rho squared sine phi. That's a little bit more complicated, but this is our conversion from rectangular to spherical coordinates. And then we pick an order of integration. We will almost always want to have rho on the inside. Okay? All right. So now let's try an example. What we would like to do is evaluate this integral over the unit sphere centered at the origin. So 1 unit in the xy direction, 1 unit in the yz direction, 1 unit in the xz direction. Okay? So we pick an order of integration. I put the rho on the inside like I said I was going to. Phi is going to give us just the angle from the North Pole to the South Pole. And so phi gives us this piece of the sphere. And then theta is what goes all the way around from 0 to 2 pi and takes this little piece and rotates it all the way around. And again, if I took the front and back of the sphere when I was counting phi, and then tried to rotate that all the way around, then I would end up overlapping it but at the halfway point. So that's why we don't want this to go to 2 pi. It avoids overlap. And then the radius goes from 0 to 1. Then we have to convert the formula inside here. X squared plus y squared plus z squared is equal to rho squared. But then that's raised to the 3/2 power. And we multiply exponents and we get rho cubed. And then here's our conversion formula, rho squared sine phi. Okay? So this is set up for us. All right. We'll do a harder setup in a moment, but this is just setting up the entire sphere. And an entire sphere, phi goes from 0 to pi, theta goes from 0 to 2 pi, and rho goes from 0 to the radius of the sphere. Okay? All right, so let's try this example. We want to sketch this region. The crazy part right here is this secant. Let's talk about what that's doing here. Okay, so let's make a table of values. One of the things I notice, though, is that this is secant of phi, and the outer limits here tell me that phi only goes from 0 to pi over 3. So I only need values that go between 0 and pi over 3 in my table. So I might include pi over 6 and pi over 4. And now let's look at the radius. Okay? So secant of phi is going to be 1 over the cosine of phi. And so 1 over cosine of 0 is 1. All right. Pi over 6. Cosine of pi over 6 is root 3 over 2. 1 over that is going to be 2 over root 3. Or that simplifies or rationalizes to multiply by root 3 over 3, 2 root 3 over 3. And that's roughly about 1.2. And then pi over 4, cosine of pi over 4 is root 2 over 2. Rho then is 2 over root 2, which rationalizes to just root 2, and that's about 1.4. And then pi over 3, cosine of pi over 3 is 1/2. Rho is going to be 2. 1 over 1/2. Okay, so let's see if we can sketch that. When phi is equal to 0, which is straight up in the z direction, phi is the angle from the positive z-axis, we go out a radius of 1 unit. From the origin. Then as phi increases to pi over 6, the radius increases to 1.2. So we travel a little bit further along this direction, but we end up at exactly the same z height as we did before. That is, that this distance is longer than this distance, but it ends up at exactly the same z height as it did before. And because theta goes from 0 to 2 pi, we go all the way around in the xy direction. That's where I'm using the 2 pi here. Then when theta is equal to pi over 4, we go, our angle is a little 45 degrees now, but we go out a distance of square root of 2, and we end up at the same z height that we did before. And then finally, when theta is pi over 3, our angle is now 60 degrees. And again, we end up at the same z height as we did before. And so what's happening is that we're creating a flat top for a cone that is 60 degrees from the z-axis in all directions. Okay? So this region looks like, I'm just going to redraw it now that we know what this looks like, 60 degrees. And then rotates around and then comes back down, and it's flat across the top. Okay? So this is the integral over a cone. Okay? All right, let's keep going. Let's find the volume of the solid that lies above the cone, phi equals pi over 3, and below the sphere, rho equals 1. Okay? So let me draw this shape for a moment. It reminds me of a snow cone a little bit. And I'll show you why in a moment. Phi equals pi over 3 means that from the z-axis we go down pi over 3. But in this equation, there is no theta, so theta can be any value. So we can go around any amount. And phi is not specified, so we can go out any amount. So this is a cone that goes out forever and around forever. but at the angle of pi over 3. So this is a cone that just goes on forever. The sphere rho equals 1 says we go from the origin 1 unit away at every possible combination of angles. And so that creates the sphere. The stuff that lies above the cone and below the sphere is this piece right here. Okay, I'm going to again draw this again just to show just the piece that we're looking at. That part is a cone, and then we have this sphere that forms the top of the cone. And so that's what happens. Sphere coming down to where it meets the cone, and then flat the rest of the way down. Okay? So if we wanted to find the volume, we have to pick an order of integration. I put the phi on the inside. Normally for volume, we would integrate a 1, but that 1 we have to multiply by rho squared sine phi. Okay. All right. Theta goes all the way around this shape. So that theta goes from 0 to 2 pi. Okay. All right. So now how do we set up this part here? Okay. If we try to use the wire metaphor, group the wrong ones together. Our wire extends in the rho direction, and it's moving in the phi direction. In other words, the wire extends along the z-axis, but instead of moving in a linear fashion, it's rotating. It's moving down like so until we exit the shape. And so we start at an angle of 0, we keep going through the sphere, but then once we hit this edge of the cone, we stop. And so we stop at pi over 3. We can still do this by thinking of a moving wire, but the wire in this case is not moving along an axis, it's moving along an angle. And so the wire is just rotating from the z-axis until we exit the shape. And now we're going to just look at what happens to the radius. If we start at the origin and just travel outwards, we always leave at the top of this sphere, and the radius stops at 1. So we go from 0 to 1. Okay? So that's a formula to find the volume of the solid. And then we could integrate that to work out the answer. Okay? Let's sketch the following region of integration. See what we get here. I don't see any crazy things like a secant in this problem, so I'm hoping that this is going to work out nicely. Okay. But one of the things I do notice right off the bat is that theta goes from negative pi up to 0. And so my angles for theta are back here. This is theta equals negative pi up to theta equals 0. So whatever we're looking at something that is on the negative y side of this graph. Phi goes from pi over 4 to pi over 2. So phi starts up here. Pi over 4 is 45 degrees down, all the way to 90 degrees down. So just within this band of angles here. And the radius goes from 0 out to 2. So what we're doing is we're going 2 units out, 2 units out, and only along the back. Okay? So I've sketched this, but this is a little hard to envision what's going on here. It's maybe if I drew it from a different point of view. It's a round base, semicircular base, that curves up. This is an overhead view. So it's a round base that curves up to this point, but then goes straight down from that point from there. Okay? So it's kind of like, it's the slice of an apple, or something like that, where we have the rounded outside of the apple, but the flat side that it's sliced along, if that makes any sense. That's the shape that we're looking at. Okay? All right. Let's look at number 5. Let's convert this integral to spherical coordinates. This looks really messy in the way that it's been given to us. So to convert this, let's go ahead and write out what our bounds are. X goes from 0 to 3. Y goes from square root of 9 minus x squared to negative square root of 9 minus x squared. And I'm going to go ahead and just combine those to y squared equals 9 minus x squared, or x squared plus y squared equals 9. And then z goes from square root of 18 minus y squared, x squared minus y squared, as an x, to z equals the square root of x squared minus y squared. All right. So this is a circle of radius 3 in the xy plane. But the x-coordinate only goes from 0 to positive 3, not from negative 3 to 3. The y-coordinate goes from the negative side to the positive side of the circle, but the x-coordinate only goes through the positive side of the circle. So not the back half. Okay? And since z is not present in this equation, we have half of a cylinder here. So that's what this boundary looks like. All right, within that boundary here, this is, if I square both sides, I get z squared equals x squared or sorry, equals 18 minus x squared minus y squared. Or x squared plus y squared plus z squared equals to 18. And that's a sphere of radius square root of 18, which is bigger than 3. So what we have here is sphere that has a radius of square root of 18 that would extend outside this cylinder here. Would keep going. But the top is going to be this sphere. And the bottom, we've seen this before. This is z squared equals x squared plus y squared, which is the same thing as z squared minus x squared minus y squared equals 0. That 0 makes this a cone. And so underneath this shape is going to be a cone. And so we're going to look, this turns out to be the snow cone again. It starts at the bottom, it opens upwards, but it has a sphere on top, and the cylinder is there to enclose where the top part and the bottom part meet together. Okay? What is this angle here? Inside the cone. How far down does that cone open up? How could we figure that out? We could figure that out by plotting a couple of points. Let's pick an example. If x is equal to 1 and y is equal to 0, then z is also equal to 1. Because 1 squared minus 1 squared minus 0 squared is equal to 0. So x goes out 1 unit, z goes up 1 unit, and y goes out 0 units. This triangle is a 1-1 triangle. I mean, the legs are 1 and 1. That's a 45-degree angle. And so this angle here is going to be pi over 4. From the z-axis. Okay? We could figure that out just by using basic trig and picking out some points. So I think we have enough information to set this up now. Put our rho on the inside, put our angles on the outside. Theta only goes from the front half of this shape. So from negative pi over 2 through 0 up to positive pi over 2. The phi starts up here in the positive z direction, and this point stays fixed while the wire rotates downwards, and it stops being inside this shape when we reach the edge of the cone, and that's at pi over 4. And then within that range, from 0 to pi over 4, if I move out in the rho direction, I always leave along the top part of this curved sphere, which has a radius of square root of 18. And then the last thing we have to do is convert this. This is rho squared, but I have to multiply it by my conversion factor, which is rho squared sine phi. And so this just becomes rho to the 4th sine phi. And now this is in spherical coordinates. All right. Let's wrap this up. I think we can do 2 more examples. Number 6. Let E be the solid inside the sphere rho equals 2. So that's just a sphere with a radius of 2. And above the plane, z equals 1. So the only part that we're interested in is this part of the sphere. Okay? We want to set up a triple integral to find the volume of that shape. Okay? Now again, volume would normally be integrating a 1 here, but we still have to put rho squared sine phi. And now we have to figure out what in the world are we going to do to get this shape in spherical coordinates. Okay? All right. Theta goes all the way around the sphere in this direction. And so we go from 0 to 2 pi. Phi is going to be a little bit trickier. Phi, when we set up bounds for phi, our wire starts at the z-axis. This point stays fixed, but the wire rotates down until we reach this point right here. So let's talk about how we figure out what that point is. Okay? So we have right here a triangle where the height of the triangle here is 1 because z is 1 unit above the origin. But this radius is out to the edge of the sphere. This radius is 2. And so this is going to be the angle we're looking for. Well, this is the adjacent side and the hypotenuse. So the adjacent side over the hypotenuse is 1 over 2. That's the cosine of phi. And if the cosine of phi is 1 over 2, then phi is pi over 3. And so we're going from 0 up to pi over 3. Okay? And now we've got the hard part here of how do we write the plane z equals 1 in terms of phi. That is, as we move out in the radius direction, we start at 0 and we end along z equals 1. But if we remember the conversion formulas we had, z is the same thing as rho cosine phi. And so we can write rho cosine phi equals 1. And we're trying to solve for rho. And so rho is equal to 1 over cosine phi. And that's the same as secant phi, which we saw at the beginning in a different example. We started with the secant phi, worked our way back to find that it was a flat surface. Now we're starting with a flat surface and deriving that it turns out to be secant of phi. And we're getting results that match in both cases. Okay? All right. And so this is a setup to find the volume of this shape. Let's move on. Last one, number 7. Find the volume of the smaller wedge cut out from a sphere of radius 2. So again, we're looking at a sphere of radius 2. All right, that's not a very good drawing, but that's okay. By two planes that intersect along a diameter. So the easiest diameter to use is just a one that goes from the North Pole to the South Pole. So the two planes that intersect along the diameter at an angle of pi over 6. So the angle between these is pi over 6. And this plane cuts off a piece of the sphere like so. And then this plane cuts off a piece like so. And again, we get one of these little apple slice kind of pieces between these things. We want to find the volume of that small wedge, not the big piece that's left over, but the small wedge that's cut out. Okay? Can we set that up? Again, this is a volume problem, so we're just taking a 1 and multiplying it by rho squared sine phi. My theta goes around in the xy plane, and we only want to go around pi over 6 this time. We don't want to go the whole way around, but we do want to go all the way from the top to the bottom of the sphere. And so phi is going to go from 0 to pi, and the radius goes from 0 to 2 along this apple slice. We want to go from the origin out to the edges of wherever that slice is. Okay? And then if we integrate that, we'll have the volume we're looking for. All right? You have 2 episigns that are due this week and a practice test to start working on. I'll see you Wednesday. Bring questions, all right? Y'all take care.